let's recap a few features that we've learned about the hydroboration oxidation and also talk about stereochemistry. The first, it's anti-Markovnikov. The second, there's no carbocation intermediate, so no rearrangement. Third, in terms of the stereochemistry, the hydrogen and BH2 add syn across the double bond. The term syn is really just kind of another way to say cis. Both groups add from the same side. And what that means is after the BH2 is oxidized, that means the H and the OH end up syn or cis. If we have this example here where we have an alkene in the ring, what you want to do is analyze both carbons and find the one that is more substituted. That's where your H will end up. And find the one that is less substituted, and that's where your OH will end up. So now to draw your products, you want to make sure you put the H and OH syn, meaning in the same direction, but they can add syn from the front or the back. So here is our 5-membered ring. If the two groups come in from the front, I'll put the H on a wedge, the OH on a wedge, and this methyl group that was there previously will end up going back as a dash. The other product will have the H and OH back. And the methyl group will be a wedge. Now, of course, you don't have to draw the hydrogens in, so it will be equally valid to draw the products like this. And you should be able to recognize that this is a pair of enantiomers. So why does the H and BH2 add syn? Well, if we think about the double bond, I'm going to write a double bond here kind of in the plane of the page. Remember, it's planar. So let's just put a group out towards us, maybe a hydrogen back away from us. And then on this carbon on the right, I'll give it a couple of groups out and back. So when that BH2 comes, or BH3 comes in, all of those atoms are connected together. So it would be really difficult, or I should say impossible, to add a boron to one side and then somehow have this hydrogen reach over and add to the other side. Instead, they have to add from the same side, so we would put the boron on one carbon, the hydrogen on the other, but they're coming from the same face. So everything can come in from the top or from the bottom side. Let's do just a couple of other examples together. This first one has a chiral center. We have our double bond. That's where the reaction is taking place. And a good idea is just to pick what you're going to keep in the plane. And the easiest thing here, let's just keep our main horizontal zigzag chain, our planar group. So I just abbreviated hydroboration oxidation. And we have our less substituted carbon right here. So that's where the OH will go. We have our more substituted carbon here. That's where our hydrogen will go. So now when you draw the product, keep that main chain exactly how we had it. The double bond, of course, goes away. Also, that chiral center where we have the ethyl group, don't touch it. We're not doing a reaction there. Leave that alone. So there's that. Then we have the reaction taking place at these two carbons. So let's say both groups come in from the front, the H and the BH2. That means we're going to have the OH on a wedge and hydrogen on a wedge. Again, remember we put our dashes and wedges on the large angle of the bond. We usually don't put them in the small angle here. So I really don't like to see the hydrogen drawn like that. Don't forget also, we have this methyl group. That's still there. Two bonds are in the plane. One bond is the wedge, so the methyl must be just a dash. Then your other stereoisomer will still have our same main chain here in red. The ethyl group, again, don't mess with it. And then we have the OH back and the hydrogen back. Those need to be syn. That means the methyl group on this carbon will be out. So now we've actually formed two new chiral centers in the product. We have one chiral center that stays the same. The other two are inverted. These represent a pair of diastereomers. Okay, let's do one other example. Here we have this chain with the double bond in the middle, but what you should recognize is that both of these carbons have the same substitution. Okay, that doesn't mean you're not going to get a reaction, but it does mean you're not going to get selectivity. Meaning you're going to have H added here and OH here, and vice versa, H here and OH here. So let's draw the outcomes of that. Okay, so here's our two carbons. The H and the OH, I'll add the H to the left carbon. I'm not going to draw it in. That doesn't form a new chiral center, so it doesn't really matter. We'll just leave it implied. And then I'll draw the OH. And then if the H and OH add to that same carbon, but from the back, we get this product. But you can also get the other isomer where the OH adds to this carbon and the H adds to this carbon. So then we're adding the H here, and then the OH we'll put as a wedge there. You can also add from the other side. You get that. So these two are enantiomers. These two are enantiomers. But if you compare the ones on the left and the right, those are constitutional isomers. So because we don't get Markovnikov selectivity, we actually end up with 4 products in this bottom reaction.